Hello friends, in last lecture we will discuss the crystal field in octahedral complexes or the crystal field splitting in octahedral complexes and crystal field splitting in tetrahedral complexes. Now in this lecture we will discuss the factors affecting crystal field splitting in octahedral complexes or the factors affecting crystal field splitting in octahedral complexes. Which factors affect the crystal field splitting or which factor does not affect the crystal field splitting is discussed in this lecture. The first factor is nature of metal ion. The nature of metal ion is very important factor because metal ion is the center of the splitting of d orbital. Hence, it is very important to study the nature of metal ion in a crystal field splitting. In this topic or the subheading of the nature of metal atom is see here the first subheading, different charge on cation of the same metal. Different charge on cation of the same metal. It means that the different charge of the cations is the same. Two central metal atoms is the same, but the charge on the central metal atoms is different. They affect higher the charge on central metal ion, higher is the magnitude of crystal field splitting value. Higher is the charge or higher is the charge on the central metal atoms, higher is the magnitude of the crystal field splitting value of that complexes. It means that, for example, two metal atoms of the same transition metal atom is the same, but different charge on the central metal atom, +2 and the +3. Then it affects the magnitude of the crystal field splitting value. See here the first example, COH26 dipositive. COH26 dipositive. It shows the delta octahedral is equal to 9300 centimeter inverse, and the same COH26 tripositive delta octahedral 20,716 centimeter inverse is a crystal field splitting or this crystal field splitting value. See here what happened. The central metal atom is the same. Here is the central metal atom is the same. The charge on the CO is a +2. Charge on the CO is +2, and here charge on the CO is a +3. It means that higher the charge, where is higher the charge? Here is the higher the charge. +3 is higher, +2 is the lower. Those central metal atoms having the higher charge, it shows the higher crystal field splitting value. CO present in the tripositive complexes, it shows the higher crystal field stabilization value or crystal field splitting value, 20,760 centimeter inverse. The central metal atom is the same, cobalt, H2O, H2, but only difference in the charge. Here is the +2 charge, here is the +3 charge. Here is the charge is more, then crystal field stabilization splitting energy is more. The second example, see here, vanadium dipositive D316. Vanadium dipositive D316 having the delta octahedral value is 12,600 centimeter inverse, and vanadium present in a tripositive complex or tripositive oxidation state having D316. Having D316, D216, not a D316, D216. See here, delta octahedral is equal to 17,700 centimeter inverse value of the crystal field splitting value. It means that same central metal atom is the same, vanadium. Charge on the central metal atom first is a 2 and second is the +3. It means that charge is greater the crystal field splitting energy or the crystal field energy is greater. It means that this occurs because of the higher the charge on the central metal atoms or higher the charge on the central metal atoms, it approaches or the ligand approaches or more closer to the central metal atoms, and the electrostatic field created by the ligand is a very greater, or great electrostatic field is created by the ligand is great, hence thereby increase in the crystal field splitting, or there is increase in the crystal field splitting when the charge of the centimeter atom is higher. This is the first factor. The second factor is the B factor. Same charge on the cation of the different metal. Same charge on cation of the different metal. Charge is same, but central metal atom is different. It means that there is a different electrons present in the d orbital. There is a different electron present in a d orbital, and this magnitude of d on the basis of this d electron, the magnitude of the crystal field splitting is decreases. Magnitude of the crystal field splitting decreases with increase in d electron. The number of d electrons or the number of d electrons present in d orbital is increases. There is a decrease of the magnitude of the crystal field splitting. Crystal field splitting is decreases when the number of d electrons is increasing. See here the one example: COH26 dipositive B716. In this, CO consists of the how many electrons? 7 electrons present in d orbital. The magnitude of crystal field is 9300 centimeter inverse. The second example is NiH26 dipositive. The charge on the centimeter atom is the same. See here, the charge on the centimeter atom is the same, +2 charge on both the complexes. But the centimeter atom is different. Here is the cobalt, here is the nickel. Of the electron present in the d orbital is different. In cobalt, the 7 electron present in d orbital. In nickel, the 8 electron present in a d orbital. Hence, number of d electron is increases. There is decrease in the crystal field or magnitude of the crystal field splitting. See here, the number of electron 8. Here is the number of electron 7. Here is increase in number of d electrons. Here decrease the crystal field splitting. There is a value of decrease in crystal field splitting. There is a 8500 centimeter inverse. This is the second factor, that is the same charge on the cation of the different metal. It means that different metal but charge is the same. That times the number of electron is different. Those central metal atoms having the large number of electrons, then it having the decrease in magnitude of the crystal field splitting, or the decrease in the magnitude of the crystal field splitting. Cobalt D7 electrons, nickel D8 electrons. It means that nickel consists of the electron, or the electrons present in the orbital is higher. Hence, there is a decrease in the crystal field splitting, or the magnitude of the crystal field splitting is decreases. See here, the C factor or the third factor, that is the nature of transition series. Nature of transition series. In a given series, or in a given series, 3D transition series, 4D transition series, and the 5D transition series, there is not much difference is arises in the magnitude of the crystal field splitting. But however, it is said that, or however it is noticed that from going from the 3D, 4D, and 5D, going from the 3D to 4D and 4D to 5D, 3D to 4D and 4D to 5D, there is increase of 3D to 4D, there is increase of the 30 to 40% of the magnitude of the crystal field splitting is increases. From the 4D to 5D, it is increases by the 25 to the 30% is increases in the magnitude of the crystal field splitting, because ionic charge or the ionic size from top to bottom, or from going from 3D to 5D, ionic size of CMI, ionic size of CMI is increases. Ionic size of CMI is increases. In a group, there is increase of the ionic size from top to bottom in a group. This is the top and this is the bottom. Hence, ionic size of the central metal atom is increases, and due to this ionic size increases, there is a better overlapping between the ligand orbital and the central metal orbital, or there is the central metal atoms or the ligand orbital, there is a greater overlapping, and the approach of ligand is also increases due to the increasing size of the ionic size of the CMI is increases. Hence, from top to bottom, the increase in the crystal magnitude of the crystal field energy or crystal field splitting. See here example: CO NH6 tripositive This is the 3D complexes. This is the 3D transition series complexes. Then RH is 6 tripositive. This is the 4D complex or 4D transition complexes. And IR is the 6 tripositive, which is the 5D transition series complexes. 3D, 4D, 5D. Let's see here the magnitude of the crystal field value or magnitude of the crystal field splitting is greater in this 5D transition series element or in this 5D transition series element because ionic size of the central metal atom is increases. Ionic size of the central metal atom is increases. Hence, there is increase in the magnitude of the crystal field splitting or the magnitude of the crystal field splitting increases because ionic size of the IR is greater than the cobalt and then the rhodium. CO having the smaller ionic radius than the RH and then the IR. Hence, ionic radius is increases or ionic radius is increases from the top to bottom in a group. Hence, in this series or in this 3D, 4D and 5D series, those complexes present in the 5D transition series, they show the higher splitting or the higher magnitude of the crystal field splitting due to the better overlapping of the orbital of the central metal atoms and the ligand. This is the third factor, that is the nature of transition series. See here, the next factor is the factor, that is the geometry of the complexes. That is the geometry of the complexes. How the geometry is affected on the magnitude of the crystal field splitting. The octahedral geometry having the more crystal field splitting or magnitude of the crystal field value is more than the tetrahedral complexes because in octahedral complexes there is the involvement of ligand is a 6 or 6 ligand is present in a octahedral complexes and in tetrahedral complexes only 4 ligand is present. It means that there is a geometry is affected. How it is affected? The more number of ligand is involved in the octahedral complexes, the less number of ligand is involved in the tetrahedral complexes. Hence, there is 33% decrease in the field strength. There is 33% decrease in the field strength, and due to this decrease in the field strength, there is a decrease in the magnitude of the crystal field splitting. Hence, in octahedral complexes, magnitude of the crystal field splitting is higher as compared to the tetrahedral complexes. Then second, in octahedral complexes, the ligand position in octahedral complexes or in crystal field splitting in octahedral complexes, the d orbital or the ligand position in direction of dx square, y square and dz square orbital. Ligands are directed towards the d orbital in position of the dx square, y square and dz square orbital or directly interact with the d orbital or these two d orbital. These ligands are directly interacted, but in tetrahedral complexes there is no footed at any of the d orbital or there is no any ligand is directly interacted with the d orbital and no more influence on the T2G orbital, and there is no directly effect on the T2G orbital than on the EZ orbital, and hence the tetrahedral splitting or magnitude of the tetrahedral splitting is decreases as compared to the octahedral complexes, and the square planar complexes having the greater magnitude of the crystal field splitting than the tetrahedral complexes, which means that the square planar complexes is a greater crystal field splitting than the tetrahedral complexes. This is the 2 points which is related to the geometry of the complexes. In the geometry of the complexes, it is very important to keep this mind. Octahedral complexes having the more magnitude of the crystal field splitting as compared to the tetrahedral complexes or as compared to the tetrahedral complexes, because in octahedral complexes or in octahedral complexes ligand is more or the number of ligand is more, that is the 6. In tetrahedral complexes ligand is 4 or the less number of ligand is involved. And the next factor is or the next point is the in octahedral complexes the ligand comes toward the central metal atoms in the direction of the dx square, y square and the dz square orbital. These two orbitals is called as the easy orbital, and this ligand is directly interacted with the d square, y square and the dz square orbital. In a tetrahedral complexes, there is no any direct involvement or there is no any direct interaction of the ligand orbital and the d orbital. Hence in octahedral complexes, magnitude of the crystal field splitting is greater as compared to the tetrahedral complexes. See here, the next factor is E, nature of ligand and the spectrochemical series. Nature of ligand, for example, central metal atom is the same. Central metal atom is the same, but with the different ligand. Different ligand shows the different effect of the crystal field splitting, or the value of the delta octahedral is different. Why? This is because of the different ligand, and this ligand is categorized in a strong field ligand and the weak field ligand. What is the strong field ligand? The ligand which split the d orbital strongly. The ligand which split the d orbital strongly is called as the strong field ligand, and the ligand which having the does not capacity or the does not ability to split off d orbital is, or the ligand which d orbital splitting is weakly, or the ligand which is not more strongly split up the d orbital or the weakly split up the d orbital is called as the weak field ligand. For example, the strong field ligand is Cn, CO is example of the strong field ligand, and the weak field ligand is chlorine, iodine, bromine is called as the weak field ligand. When the central metal atom is the same, is present, for example, chromium is a central metal atom. When it forms the complexes with the Cn, then there is formation of the, or there is the crystal field splitting is higher. When the chromium forms the complexes with the chlorine, the crystal field splitting is lower. These differences is arises due to the presence of the strong field ligand and the weak field ligand, and this strong field ligand and weak field ligand is responsible for the crystal field splitting in octahedral complexes. In spectrochemical series, we have made the special video on the spectrochemical series. In spectrochemical series, all the ligands are present and they are distributed in the strong field ligand and the weak field ligand and the neutral ligand.